Okay, so welcome to a speech recognition and electrical and computer engineering colloquium. Today, as a guest, we have Karen Livescu. Karen Livescu was somebody we sought and as a graduate student, but we failed, and she went instead to MIT. As Sanjeev just said, fortunately they didn't screw up, and she developed into the fantastic person we believe she will develop, and that's why we wanted her. And I should say that she got her PhD in electrical engineering at MIT in 2005. The thesis title was Feature-Based Pronunciation Modeling. She has been both a participant and a leader in two workshops, Johns Hopkins summer workshops. Last one, the previous summer, where she led a group with the title Introductory Articulatory Feature-Based Automatic Speech Recognition. And she's now a Claire Bruce postdoc lecturer at MIT, and she's going to talk on factoring speech into features. Karen Livescu.
So the work that I'll be describing today is a combination of work that I did as part of my PhD thesis, as well as work I've done since then as a postdoc, as well as including some things from last summer's summer workshop here at CLSP. So speech is a very unique signal in the sense that it's both highly complex and structured, but also highly variable. And one of the things that anybody working in speech has to deal with is the overwhelming amount of variability in speech. So just to give one example of that, I'm going to play for you a few samples of one word.
Probably or probably.
Okay, so hopefully people could tell that that was the word probably. Maybe not, but that's part of the problem. So what were the sources of variability there? There are a bunch. So for example, they varied in speaker, in channel, in acoustic environment, so things that we could sort of lump together as acoustic variability. Okay. They varied in prosody, so the choice of intonation, contour, speaking rates, speaking rate variations, dynamics, and so on. And they also varied in terms of pronunciation, so the choice of subword units that the speakers chose to use to pronounce that word, or perhaps didn't choose, and that's just the way it came out. And these are just some of the sources of variability. And so my job as a speech researcher, as I see it, is to take all kinds of data of this type, combine it with knowledge that we have from speech science and from linguistics, as well as with statistical and machine learning tools to build new models, both for speech technologies, as well as hopefully in the long term for improving our knowledge about speech itself. So most of what I'll be talking about is about speech recognition, so I want to set up the setting that most people use when they do speech recognition, which is broadly speaking, a generative statistical setting. Okay, so we have a generative model for how we go from words to acoustics, and it goes something like this. We break it up into a number of factors. So first we assume that we have a language model, which is essentially a distribution over word strings. So the language model generates a word string. Given that word string, we have a pronunciation model, which is essentially a model of some set of subword variables, which are not heard. They're hidden, some kind of hidden state variables. And there are many forms that these variables can take. For example, they can be subphone states. And given that set of state variables, we have an observation model that generates an actual acoustic observation from these states. And the acoustic observation is typically a set of equal sized, usually about 10 millisecond long, frames consisting of some type of spectral parameters. Okay. And the task of a speech recognizer is to find the most likely string of words given the acoustics, which we can break up into a product of the three terms that I just talked about. And the term that I'll be focusing on mostly today is the pronunciation model. Okay, so probability of Q given W. Okay, so the first problem in dealing with pronunciation models is what is Q? Okay, normally Q is a string of phones or subphone states, and what I mean by phones is if you look up the pronunciation of a word in a dictionary, the string of symbols that you would see there for that word are roughly speaking phones. Okay. But unlike a string of phones, when we actually produce speech, it's made up of this sort of delicate dance of articulators that are somehow trying to reach certain targets, but not necessarily doing it in as coordinated a way as we might hope. So what I'm going to talk about today is a way of taking advantage of what we know about the states of the articulators during speech to do a better job of predicting pronunciation variability. Okay. So the main contributions of this work are this new approach itself of breaking up words into features to predict pronunciation variation. And what this gives us is parsimony over phone-based models, as well as linguistic interpretability. So using a model like this, we have a way of interpreting what was going on under the hood when this person was speaking this word. Okay. And second, the implementation of the model is non-trivial. It's, in this case, using dynamic Bayesian networks. And what this framework gives us is both learnability. So the parameters of the model can be learned from data, as well as a way of fitting it fairly seamlessly into the standard generative statistical setting of speech recognition. Okay, so just an overview of the rest of the talk. I'll give you a bit more background about phones and features and pronunciations. I'll talk about the models and their implementation, and I'll give you a sampling of experimental results from different types of tasks, and also talk about some ongoing directions in future work. So going back to the pronunciation modeling problem. So here are a few words, and so these are 4 words along with their dictionary or base form pronunciations, and all of the ways that they have been pronounced in a particular small database, or not so small, a couple of hours database of manually transcribed speech, okay, along with the number of times that each pronunciation occurred. Okay. So what are the things that sort of jump out immediately when we look at this? So first, there's a huge number of different pronunciations per word. Each pronunciation tends to occur very rarely. The dictionary pronunciation itself almost never occurs. It only occurs in 4 out of 89 instances of the word don't. For the other words, the dictionary pronunciation never occurred in this data. And the pronunciations themselves are quite different from the dictionary pronunciation. There's a couple of these that I'm going to come back to later. Just as an example, I'll come back to these 2 pronunciations of the word sense. In one case, it seems like it's had a T inserted. In another case, it's been quite mangled. Okay, but not so badly, you'll see. And just to convince you that it's not just a matter of these 4 words, if we look at the number of different distinct pronunciations per word as a function of the minimum frequency of that word in this database, it looks something like this. So if a word has been pronounced at least 50 times, then it has about 35 distinct pronunciations. Okay. So there's a huge number of distinct pronunciations per word. Okay. So hopefully I've convinced you that there is a lot of variability.
This is independent of the word?
This is just an average over all words that occurred at least 50 times. So.
And another question, I guess, is that for example, for the word don't, one of its pronunciations is O, and another one is So you're saying that if you played back that sentence, let's say ±2 seconds, that I would recognize that the word is different. That it's not like...
You would certainly, so you wouldn't in all cases recognize the word. And I think probably in those instances of probably that I played, you also probably wouldn't have recognized the word.
No, that's because you played only the word. If you played a couple of seconds.
Whereas if you played the entire sentence,
that's what I mean.
in virtually all of these cases, Yes.
Right, the language.
How many people? How many speakers?
It's timid, right? I mean, it's just timid.
This is switchboard. This is the manually transcribed portion of switchboard. For Timid, it's not quite this bad. We would have the graph would look something like this. Tens of speakers. I'm not sure exactly.
So the number of different occurrences basically is really, everybody says these words in a different way.
Everybody says it in a different way, and the same speaker may say it in different ways in different contexts or in different moods. Okay. One thing is that, of course,
This is Greenberg's transcription.
This is Greenberg's transcriptions. Yeah. One thing to point out is that, of course, words are highly affected by nearby words as well, and so words like don't, or short words, are particularly subject to this. And so, in the experiments that I'll show, I actually cut out particularly short words like don't that have a high chance of being mostly affected by nearby words rather than by word internal effects. Okay. And it's sure. And it's not just that there's a huge amount of pronunciation variability, it's also that we know that it does affect speech recognition. So, for example, we know that words that are produced differently from the dictionary pronunciation are more likely to be misrecognized, and conversational speech, which is characterized by a lot more pronunciation variation, is recognized at twice the error rate of read speech, even when produced by the same speakers in the same acoustic conditions speaking exactly the same transcripts. Okay. So pronunciation variation is an independent factor for the poor performance of speech recognizers. Okay. So let's talk a little bit about the dominant paradigm to pronunciation modeling, which is phone-based. And how might you generate new pronunciations for words in a phone-based way? Well, you would probably have the dictionary pronunciation of the word, and then you might have some kind of phonetic confusion rule, an insertion, deletion, or substitution rule that generates alternative pronunciations. And you can have a large set of these. Usually they're of the form, some underlying phone goes to some surface or actually produced phone in some left context and some right context. And these rules are either derived from linguistic knowledge or they can be learned from data. But some of the issues that have come up with this kind of modeling are first, sparse data issues. There seems to never be enough data to actually see enough of these phonetic contexts to get a robust model. Low coverage of conversational pronunciation. So despite all of the work that's been done in pronunciation modeling, still we can't account for most of the conversational pronunciations that we see. Okay, and I'll show that in the experiments. Also, many pronunciation changes are not really wholesale phonetic changes. Some of them are sort of partial changes. And this is completely not handled in phone-based pronunciation models and tends to wind up with more interword confusability. Okay, because more words are now starting to have the same pronunciations. Okay, and finally, in terms of experiments, there just hasn't been that much improvement in speech recognition over the past 10 or so years of doing these kinds of pronunciation models. So looking a little bit under the hood of speech, so let's look at what some of these articulatory features look like. Phonologists are, like articulatory phonologists, autosegmental phonologists, tend to describe speech in terms of multiple streams of some kind of subphonetic feature. What that is can vary. What I'm showing here is a feature set that's based on articulatory phonology, so it's based on a fairly detailed description of what the lips are doing, different parts of the tongue are doing, the glottis or the vocal cords, and the velum or the soft palate, which controls how much air flows to the oral cavity versus the nasal cavity. Okay. And the exact values of the features are not terribly important. I wanted to show the feature set just so you have a sense of what the state space is. Okay, so for most features, there's between 2 and 8 values, okay, that tend to get used in articulatory phonology. And this is the feature set that I'll be using for most of the work that I'm showing. Okay. So let's go back to one of those examples. So let's think about the word sense, pronounced as if it's had a T inserted. Okay. So let's think about what happens when you're nearing the end of the word, so you've just produced the N, and you want to produce the S. So what are the things that your articulators have to do? Okay. So first of all, N is a nasal voiced sound, produced with the tongue tip teeth, making a closure behind the teeth. An S is a non-nasal, voiceless sound produced with a slight opening of the tongue in the same position. Okay, so there are three changes that have to occur. You have to stop nasalizing, stop voicing, and slightly move the tongue. Okay. So in a phone-based view, what happens is the brain orders up an S, and supposedly all of the articulators spring into action and produce this S. What might happen in practice is the brain orders up the S, the velum and the glottis, so nasality and voicing spring into action right away. The tongue might take a little bit longer. In this case, the lips aren't involved at all. Okay, so what happened there? Okay, so we wound up with a situation where the velum and the glottis have reacted. So what that means is we have a non-nasal, voiceless sound, but with the same tongue position as an N, which just happens to be a T. Okay. So for that brief period of time, it appears that a T is being produced. And this is an extremely common phenomenon. It doesn't only happen with N and S, it happens with various nasals followed by various fricatives. So rather than having a whole set of phonetic rules that say what are the possible phonetic changes in various contexts, we have one rule that says these two articulators can desynchronize slightly from this articulator. So that gives a sense of why these kinds of models might be more parsimonious than phone-based models. Okay, and looking at it in just a little bit more detail, here's that same example with all of the feature values written out. So this is what the dictionary would look like. We would have, if it's a phonetic dictionary, this would be the phonetic base form. If it was a feature-based dictionary, we'd have multiple streams of features. And here's what that surface pronunciation looks like. In terms of phones, it looks like we've inserted a T. In terms of features, all of the feature values have actually stayed the same, and the only change is that there's been a slight shifting of boundaries.
You mean that's what actually happened? Is that what you're saying? I don't know what surface means.
Oh, surface means what was actually produced.
Yeah, that's what I said.
Yeah. Okay, so that's the one that we just looked at. What about that other one? So sense being pronounced purportedly like sits. Okay. Well, so if you look at it phonetically, it looks like most of the phones have been completely mangled. If we look at the articulators, what we have is a bit more of this boundary shifting and just a tiny, gradual shift in a couple of the feature values. So again, much less in terms of feature variation than phone variation, yes?
So this is really, you're inferring the articulators just from the phones that you actually observe. You don't really record the articulators.
Right.
You mentioned them and figure out whether that's true or not.
Yeah. What I'm saying is if the articulators were to do this, it would give us the phonetic transcription that we see. And we can have what looks like a simpler description in this way than in terms of phonetic transformations. Okay. So how do we put these ideas into a model? Okay. So first, just the main ideas of a model without any implementation details. So we start with a base form dictionary like everybody does. We have, suppose the word is everybody. We have the phone sequence. We convert it into these multiple streams of features. And there are two kinds of processes that we're going to allow in going from this underlying pronunciation to the surface pronunciation. So the first one is asynchrony between the features. And what this means is that all of the features are going to go through the same set of state indices. So all of them are going to go through their first state, followed by their second state, and so on, but not necessarily at the same rate. Okay. So here I'm showing two features. So this is saying the glottis is spending 4 frames in the first state, 3 frames in the second state, and so on. The lip opening feature.
When you say state, you mean like the final one is the one it's aiming at, and there are some natural transition states?
What I mean by states is just, I actually mean phonetic states. So each of the articulators is trying to reach the phonetic targets for the N phones in the word.
Yeah, and the trajectory is the quote natural trajectory to go from the beginning to the end. Is that right?
Yeah, but what I'm talking about here is just how fast does it go through that sequence of N or states. Okay. So what we call asynchrony is when two features are in different state indices at the same time. Okay. So in this case, we have 2 frames where we have asynchrony between those two
So
features.
again, just to clarify, so what this says is, let's say the first one is the glottis and the second one is the lip opening.
Right.
So the 4 zeros on glottis indicates that it is where it needs to be to produce the air.
Exactly.
The 3 ones indicate that it's where it needs to be to produce the ver, and the 5 twos indicate that that's where it needs to be to produce the
Exactly.
And then at the same time, the lip opening. So what has happened here is that the lip opening in the second set of ones, it hasn't gotten to 2 yet. To get the canonical pronunciation, it should have spent 3 units of time in 1 and 5 in 2, but it's just a little late yet.
Exactly.
And the 0, 1, 2 should be mapped back to
Should
the
be mapped back
phone
to here,
sequence.
right?
Okay.
So this means the glottis should be critical, 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 which is not very interesting,
Okay.
but the lip open should be wide, critical, narrow.
Okay. And it took time to go from critical to narrow.
Exactly, yeah.
So there's something about the example that's bothering me, which is you show it switching indices early in the glottis, but not changing its behavior.
Yeah, so this example is a little bit degenerate in that sense.
Okay.
When it doesn't actually change its behavior at boundaries, it's not very meaningful to talk about whether it's asynchronous from the other features.
But you sum over the possible segmentations.
We do sum over the possible segmentation, so we sum over.
Yes.
Oh, maybe I'm misreading. So it's the lips that are late, not the glottis that changes early.
That's right.
I'm sorry.
It actually doesn't matter which way you look at it.
Well, it does from the point of view of the program, doesn't it?
It might matter because you might have some distribution over how long you send each
Right, so
segment.
if you have a duration distribution, then it starts to matter whether one is late or the other one is early.
Yeah, because if I'm going to interpret this as delay due to inertia versus anticipation, which is a central phenomenon,
Right.
then it would really make a difference.
Right. We don't differentiate between one or the other. Okay, so the way we define the degree of asynchrony between two features is just the absolute value of the difference between their indices. So if we wanted to differentiate between those two situations, we would have different distributions for positive versus negative values.
That would matter.
I'm sorry.
It's just the same, just by finding the absolute value. It's taking away a lot of things.
You mean by having the absolute
Yeah,
value
instead
rather
of-
than?
yeah.
Yeah, absolutely, absolutely. So this is quite a simple model.
Okay.
Yeah. Okay, and then we have a distribution over the allowed degrees of asynchrony. And the second type of variation that we're going to allow is what we're going to call feature substitution. So it's basically when a feature doesn't reach its target value. Okay. So for example, if we just look at the lip open variable, for this particular example, it should have gone from wide, critical, narrow, but the surface values might be a couple of frames of wide, a few frames of narrow, and then finally critical. Okay. And so these are frames where we would say that a feature substitution has happened. And we also have a distribution over the possible surface feature values given the underlying feature values. Okay. And for now, we are using a context-independent model here. Of course, this is also something that's highly context-dependent, and that's a subject of ongoing work.
So is this what Fred was asking, that it goes through its natural physical motions in order to get from W to N, W to C, which is that it tends to undershoot, become narrow,
Right.
and then come back?
Right, right. So that's where a case where the actual value of the feature changes as opposed to the time. Okay, so how do we actually implement this? We're going to use a dynamic Bayesian network model, and I'll give just a very brief introduction to what we mean by that. So a Bayesian network is a way of representing some distribution over a set of, some joint distribution over a set of variables using a graph, where each node in the graph corresponds to one variable and its distribution given its parents in the graph. And the node, the edges or the lack thereof represents the independence properties that we assume to exist between variables. Okay, so in this case, for example, we have 3 variables. This variable has a distribution of its value given its parent. This variable has 2 parents, so we have a distribution of C given A and B. Okay, and the joint distribution of all of the variables is just the product of these 3 factors. Okay. So that's a Bayesian network, and a dynamic Bayesian network is simply a Bayesian network that happens to have a repeating structure. And we refer to the repeating unit as a frame, which is coincidentally happens to correspond to a speech frame in speech models. And so an example of that is a hidden Markov model. So this is what a dynamic Bayesian network for a hidden Markov model would look like. In every frame, we would have just two variables, the state variable and the observation variable. And we would have the transition probabilities encoded as the distribution of the state variable, and the observation probabilities are the distribution of the observation variable. And the joint probability over all the variables, as we know, is just the product of the state transition and the observation probabilities over all frames. Okay. And one of the nice things about dynamic Bayesian networks is that they have standard algorithms for all kinds of computations that you might want to do that fall under the name of statistical inference. So you might want to infer the most likely values of some of the variables given the others. So that's just a generalization of Viterbi decoding in HMMs. You might want to learn the values of the parameters using expectation maximization, generalization of Baum-Welch. But we have standard algorithms for doing this for an arbitrary dynamic Bayesian network. Okay. So how do we actually encode the type of model that I just described as a dynamic Bayesian network? So what I'll do is I'll just keep this here as a reminder of what are the things that we're trying to model. Okay. And I'll bring up the dynamic Bayesian network variable by variable for 2 frames at a time. Okay. So first variable we want to keep track of is just the value of the word in every frame. Then we want to know, so this is an example assuming that we have 3 features. So then we want to know what are these state indices, the 0, 1, 2s that we were looking at before for each of our 3 feature streams. Given the word variables and the index variables, we have a distribution which may or may not be deterministic over the underlying or the target states.
Excuse me, is the int a string or is the int one of these things?
Int is just one integer, 0, 1.
So it's one of the columns there.
Int is
The heading of
it's
one of
of
the
these
columns.
guys.
Yeah, that's what I mean.
Yeah.
And the words is the same word.
Usually it's the same word for 2 frames in a row.
Yes, yes. Oh, this is per frame.
This is per frame. So,
I see.
so
Okay,
this is
fine.
1 frame, this is the second frame.
Okay.
Okay. So given the word and the index value, we can just look up what the underlying value of a feature is in the dictionary, which may also be a distribution. We might say that some feature can take on a distribution of values at a given point in the word. Okay. And given the underlying feature values, we have a distribution over the surface feature values, which, because we've made it context independent, is just a confusion matrix. And this is a typical type of structure for one of these confusion matrices where they tend to have zeros below the diagonal, meaning that usually a feature goes from a more constricted value to a less constricted value. So usually we don't go from, say, closed, from critical to closed, but we might go from close to critical. So we tend to relax the values of the features.
Excuse me, Karen.
Yeah.
What is S again in that matrix? It's
So-
one of the CL, C, or N, or?
Exactly. So each feature, so say lip opening, has an underlying value that could be closed, critical, narrow, and so on.
Okay, that's in the first
Right.
first matrix.
And that's what we have here. And the surface values typically range among the same set of values. We just have a confusion matrix from given what the underlying value is, what's the distribution over the surface values. So these are the values that are actually produced.
U is sort of the intended.
So these are probabilities, are they? And
These are probabilities. Yeah.
and the fact that they are both 7.2.1
Is arbitrary.
is a coincidence.
Yeah.
In other words, it could be in first row 0.7, 0.2, 0.1, and second row something else, but it will have to sum to 1.
Exactly.
Right.
Right. So this variable is this stream down here, and this variable is this stream. Okay. And then we have the same kind of structure for all 3 of our features. And we haven't said anything about how we're going to implement this asynchrony modeling. So the way that we do that is for every pair of features that we have one of these soft synchrony constraints, we have a child variable of the 2 index variables. And I will not go into the details of implementing that, except to say that these special variables are always observed with value 1, and their distribution is just set up in a special way as to have the probability of that value happen to be the probability of these 2 indices being at this degree of asynchrony that they are. Okay. Yes.
You also have synchrony between 1 and 3.
We could. It's a design choice.
Another question.
Yeah.
The U values, the intended values, is one of the choices don't care?
So that would be a uniform distribution. So in the dictionary, instead of having a value for it, I would have the distribution.
Okay. No, what I'm saying is in your early example, you said the lips didn't matter when you were making the N versus.
It's not that they don't matter; they just don't change. So they have to be open.
Okay. Okay. So for every phoneme, each feature has a required value. It's not like for some phonemes a certain feature doesn't matter.
You could have a don't matter.
Okay.
Yeah, I was just saying you could implement that as a uniform distribution. Okay.
So to be sure that I'm following the same question again, up to this point, your synchrony is still this absolute time difference, and you're not distinguishing between anticipatory planned co-articulation and carryover or inertial co-articulation.
That's
You're
right.
modeling those with the same thing, or are you going to later do?
In this basic model, they're anticipatory and they're modeled
Okay.
the same.
But if you wanted to do it, you could have a brain.
Yeah,
right?
it's not very complicated to model it. It's just more parameters, and we haven't put it in.
So there's nothing in the computational structure that you want to describe that really enforces a time goes positive.
No, there is. So these
Okay.
index values, the index value at this frame can either be equal to the previous or it can go up by one. Yeah.
Yeah, but also answer Jack's question, the synchronization variable sync.2, how it depends on index 1 and index 2 is fairly general, and right now you're just saying it depends on the absolute value of the difference. But for example, you could have one synchronization variable that says int1 can exceed int2 but not fall behind
Sure.
it, and that's your anticipatory movement by so much and so on and so forth. So
Yeah.
that function is fairly general. There's
Yeah,
no-
actually, the structure of the model doesn't impose the constraint that we model.
And are we thinking that, for instance, there is a probability distribution that int1, int2 is equal to the next int2, or it is one larger,
Yes.
and that's all there is to it, and they are independent of int1. I mean, there doesn't seem to be any connection.
Conditionally independent given the word. Yeah. Actually, maybe, so if we're good with this, maybe I'll go on to the next slide because I'll start to talk about independence. Okay. So I do want to make explicit what are the independence assumptions that are being made by this model. So first of all, we're assuming that the underlying feature values are conditionally independent given the word in the index. So the target trajectory of each articulator is independent of all the other articulators, assuming that we know the word that we're in. Okay. That seems like a fairly reasonable assumption. Another assumption is that the feature timing is not independent. It's dependent through these synchrony constraints. Okay, so we can enforce things like you can't have an articulator going all the way to the end of the word while another articulator is still at the beginning of the word. Okay, so we can enforce that.
We can enforce that, or cannot?
Yeah, we can, just by having appropriately placed zeros in the distribution of the sync variable. Okay. And the surface feature values are, in this particular model, conditionally independent given the underlying values. And that's the really big assumption that we're making that we really shouldn't be making. What we should probably be saying is that the surface values depend also on neighboring surface values as well as neighboring underlying values because of things like inertia and anticipation. So these, I'm drawing these arrows as dotted just to indicate that we haven't put those in yet. That's a subject of ongoing work. But for now, we make this assumption. Okay. So just a few words about related work. So there has been work done on using feature-based representations for speech recognition, and usually that work has been on observation modeling. So on the relationship between the acoustics and the feature values, not so much between the words and the feature values. There's been fairly little work done on that. And what has been done has tended to be either to use a hidden Markov model with a huge state space where each state corresponds to some combination of feature values, or to do some kind of two-pass model where we assume that we're going to first recognize the feature values and then we have some kind of decision fusion model for how we put them that I've shown do that these other models don't is that, first of all, we can use linguistic knowledge to constrain the independence assumptions that we make on the articulators, as well as not making overly strong assumptions in the way that these kinds of models do. And we're using a computational framework that we can put seamlessly into generative statistical setting, right, as opposed to something like a two-pass model. Okay, so let me get into some experiments if there are no other questions about the model. Okay, so the first kind of experiment I want to talk about is really a proof of concept experiment. So we want to abstract away from the language model, from the observation model. We want to know how good is this as a pronunciation model. Okay. So what if we pretend that we're given the values of the features as they were actually produced, and our job is to just infer the identity of the word, okay, for a single word. So no language model, no observation model. Okay. So again, we're going to use the data, the manually transcribed data from Switchboard. And what we have here is a very detailed manual phonetic transcription. It also has some diacritics like nasalization and frication, which we then convert into feature values, per frame feature values. And then for each word in the vocabulary, we use our model to compute the log probability of that word given the articulatory feature observations. So we wind up with a ranked ordering of our vocabulary by log probability, and then our hypothesis is just the most likely word. Okay? So it's a very idealized speech recognition task. Okay, so, and how do we look at the performance of these models? So there are different ways that you can imagine quantifying how well these models are doing. I'll show two measures. We've looked at a bunch. The two that I'm showing are coverage, which means did the correct word occur in the list with some non-zero probability? Okay. So the produced word the produced pronunciation is at least allowed by the dictionary. Okay. And then accuracy, which is the correct word number one in the list. Okay. So we're going to look at a few phone-based models and a few feature-based models. So the first phone-based model is just base form. So if you just take a basic
It's
dictionary,
just what?
base form dictionary. So really no pronunciation model. So it has a coverage and accuracy both of about 41%, which means about 41% of the words in our test set are pronounced like they are in the dictionary. Okay, and about 60% of the words are not pronounced as they are in the dictionary. Okay. So the next thing we tried was, what if we add...
And the accuracy is the same because no two words share a pronunciation?
Right.
Otherwise the accuracy would be less than coverage.
Yeah, we did have one word that shared a pronunciation. So we did have two words that shared a pronunciation, so it's like slightly different 40.7.
Okay.
But, okay, so then we said, okay, well, we have these phonetic rules that we've been using for the MIT speech recognizer. There's a list of something like 150 of them. What if we throw those all in? And interestingly, we are only able to cover another approximately 4% of the pronunciation. So this huge set of phonetic rules is just not generating the pronunciations that we actually see. Yep.
These are phonetic rules that phoneticians basically
Yeah.
hand produced.
Right, it's a combination of rules. They're all hand-produced, but they have been sort of honed over the years of working with speech recognition.
So they're not just based on introspection?
They're not just based on introspection, yeah.
You could imagine coming up with phonetic rules with 100% coverage
Right.
that were weighted appropriately. You know, any kind of transducer or weighted at a distance model,
Yeah.
whatever.
Yeah, so that's one number that I don't have. What would happen if we did that? Presumably it would get terrible accuracy because there would be huge confusability, but...
Well, no, and that depends on the probabilities, right? So, in a sense, you could compile down your model into a model of that form.
Absolutely.
Right, and then the question is just the parameterization of your model gets away with fewer parameters and therefore has better generalization.
Right. There's a reason why we don't do that, right? We don't usually have a speech recognizer that has all possible pronunciations occur for all possible words, because usually that tends to have high confusability. So what I've tried to do is to have phone-based pronunciation models that people actually tend to use in speech recognition. Right? So they tend not to have infinite numbers of phonetic rules allowed.
Well, let's take this off.
Okay.
You've got lots more stuff.
Okay. All right. So that's what happens when we add these phonetic rules. What happens? All right. So it looks like the phonetic rules are probably not appropriate for this task. Why don't we throw in all of the pronunciations that we've seen for all of the words in the training data? Okay, and that gets us a coverage of about 66%, which means that 34% of the words are pronounced in ways that we didn't see in the training data. Okay, we get a slightly higher accuracy. Okay, so then with a model of the type that I showed before, we're able to cover 3/4 of the words and get about 61% accuracy. And so what are these? So that's much better, and that's nice. What are these 25% words that we're not covering? We didn't try to cover everything possible because we know that we shouldn't have a pronunciation model that allows for everything with some non-zero probability. But what are these things? So these are mostly things where there are word boundary effects that we're not modeling yet because we're forcing the articulators to synchronize at the ends of words, or context effects that we're not modeling yet. So, like I said, we have a context-independent substitution model. So I think that's most of what's going on in these remaining 25%. And the last thing that we wanted to know is how important are these particular features that we chose? Okay. So most people who do feature-based pronunciation, feature-based recognition, tend to use features that are more similar to the International Phonetic Alphabet parameterization. Okay. So what if we had done that? And it turns out that there's a lot worse. Okay. So it's actually important to get the speech science part of it right. Why do they do worse? Well, probably because the assumptions that we've made about the features, about the independence of the features is not correct for that particular parameterization. Okay. So for pronunciation modeling, it seems that articulatory style features are better than International Phonetic Alphabet style features. Okay. So that's sort of a proof of concept experiment. Now, if we wanted to put this kind of model into a complete recognizer, we also need to have some kind of observation model. Okay. So I'm not going to talk a whole lot about observation models. That's not been the bulk of my work, but I want to mention what are the options. So we need a way to map from the surface feature values to the observations. And one way to do it is to just have a separate generative model, like a Gaussian mixture model, for the observation vector given all of the surface feature values. Okay. Another way of doing it is to have some kind of classifiers of features and to use their scaled outputs instead of likelihoods, right? So we could have the scaled output of the neural network, say, representing the probability of the observation given a certain single feature value. So for people familiar with hybrid hidden Markov model neural network type systems, this is simply a generalization of that. Okay. We can also use feature classifiers to generate new acoustic features, right? We could take the outputs of feature classifiers and treat those as just a transformation of our acoustic features and have some kind of generative model over those. Okay. And we've looked at all of these, and I'll just mention each experiment, which one is happening in each experiment. Yep.
So I understood the version of this where you had 01, 02, and 03 all fusing together into a single absorbed output. I don't understand how you absorb 01, 02, and 03 here separately in the picture you have now.
So here what we're saying is suppose that we have some classifier of this feature.
Of which feature?
Yeah, okay, now I
any
got
one
it.
feature.
Okay.
Like a voicing detector.
Yeah, like a voicing detector.
Okay, yeah, I got it.
And we take its outputs and we have a Gaussian mixture over those outputs.
Sure.
Okay.
And you would train those separately based on data which was hand annotated for features.
Well, so that's an issue.
Sure.
How do we train them? So that's the next bit of experiment. So how do we build these feature classifiers? Okay. So first of all, their task is given a single frame of speech, determine the value of a given feature. Okay. So how do we train them? Well, we have a bunch of acoustic observations, and we have feature transcriptions corresponding to those acoustic observations, and for each of those features we generate, we learn a classifier. Okay. Okay, so how do we determine what the ground truth values are? This is really a non-trivial problem. Okay. So one thing that we did at last summer's workshop is to try to generate articulatory feature transcriptions that allow for some asynchrony between the articulators. Okay. So one thing we can do is to generate phone labels using some static forced alignment, say, and just convert those to features. Okay. Those don't allow for the kinds of articulatory processes that we know to exist. Another thing we could do is to take some, to build a complete feature-based speech recognizer, perhaps a really bad one. We're really good at doing that. But it turns out you don't really need a really good recognizer to generate reasonable alignments. So what we did was we took a feature-based recognizer that uses a type of pronunciation model I've shown. We've just limited the word alignments to be known, and then realigned the data using the feature-based model. So now we're allowing for asynchrony between the features. And yep.
So did you do something like number one with the Greenberg label training data?
It wasn't the Greenberg training data because we wanted a lot more training data. So we actually just used automatic phonetic alignments for the Fisher data. So we had about 2,000 hours worth of training data. Okay, so these are, what I'm showing here is for each of the features, the chance accuracy, so just what is the probability of guessing the right word, the right value. What happens when we train it using a phonetic alignment, and what happens when we train it using this modified feature-based alignment? Okay. So this is kind of encouraging. So we could do a better job of aligning data using a feature-based model. And I should mention that actually the feature-based model that generated these transcriptions was actually quite poor. This indicates that perhaps these models also have other features, other applications. So if we could do a really good job of aligning data, perhaps it has applications in computational phonology or even in speech pathology if you have a sufficiently detailed model of the articulators. Yep.
But so the phone base in your system do about the same.
Well, so we're looking at these two. So we see improvements of around 5 to 10%. Okay. So the last type of experiment I want to show you is a completely different kind of task. It's a visual speech recognition task. And what do we mean by visual speech recognition? It's basically lip reading, right? We have a silent video of a speaker's mouth, and we want to recognize the words. Okay. And the nice thing about video is that you see some of the articulators. So unlike audio, there's presumably a simpler mapping between the signal and the values of the articulatory features. So in this case, we used a reduced set of features consisting of the features that correlate with lips and tongue and teeth. And just to demonstrate why we think that there is asynchrony even just among these features, if we look at these two images drawn from the sound M in two different words, so this is academic versus romantic. So hopefully you can see that that the lips are much narrower for the M in romantic.
So it's the same person?
This is the same person, yeah. And presumably that's because it's following an O, and the lips are still rounded from having just produced the O. Okay, so this is one type of asynchrony among just the lip features. Okay, so the experiment that we did was an isolated phrase recognition experiment. You can't do very good lip reading for a large vocabulary task, but you can imagine a scenario where, say, you're sitting in your car, there's too much acoustic noise to do anything useful with acoustic speech recognition, but maybe you can lip read some commands that you're giving to your car. In this case, we chose a car stereo system, and we had 20 different commands that you could give your car stereo. And the phrases were spoken at multiple speeds, so we can look at effects of training versus test speeds. And the observation model in this case happened to be Gaussian distributions over SVM classifier outputs. Okay, so we have SVM classifiers for each of these features, and then we use those basically as a transformed acoustic feature vector. We have Gaussian distributions over those. Okay? Yeah.
And for those, you don't really use any of the dynamics in the lead blocking and clause. You just use endpoints, beginning and endpoints. So how do you do that?
For the classifiers?
Yes.
They're actually just single image classifiers. So given an image, how open are the lips? How narrow are the lips?
It's a whole image, all the pixels.
It's like,
of the image.
lower.
The least, yeah.
Okay. And what we found was that a single stream model that basically collapsed all of these multiple features into a viseme, so the visual correlate of a phoneme, does a lot worse than a feature-based model that has all of these streams with some asynchrony allowed between them. And that was true across different training and testing speeds. And the best result that we were able to get is about 4 out of 5 of these phrases are recognized correctly. Okay.
Sorry, I'm not following this chart. Shouldn't there be matched conditions also between training and testing? Maybe I'm
Ideally
misreading
there
this.
would be, but we just didn't have enough data for each condition, so we always use 2 conditions in training and the third one in testing.
Okay, you
Oh,
could
well,
have.
what we could have done was to just mix up all the data and to take some random part of it for training and the rest of it for testing, and that was one condition we did.
Sure, right, exactly.
Yeah.
Or, yeah.
Yeah.
I
We
understand.
actually-
These numbers might actually be sort of artificially low, right? And it may also be that the comparison is distorted by the fact that you're asking whether these generalize well across conditions. So
Right, so
I would
what
expect that
we're-
your model would have better out-of-domain generalization performance because it's linguistically deeper. Whether that kind of generalization is necessary for training and test data or matched isn't as clear.
Right, so one thing, so if we did that, we might get better numbers down here for both kinds of systems.
And they might be closer together.
And I don't know if they'd be close. Oh, because this model might do a better job of dealing with different speed condition changes. You're right,
Yeah.
that's possible. What we were thinking we would see, and the reason that we did this separation of train and test, is that we thought that we would see different effects for different training versus test speeds. And in the end, we didn't really. That didn't actually bear out. Okay. So let me just talk for a few minutes about the ongoing work, some additional ongoing work. So like I said, some improvements in the basic model that I think have to be done before this kind of model can be used in a large-scale system is to do a really, to put a real effort into modeling context dependency and crossword effects. Okay. Another application we started to look at during the summer workshop was audio-visual speech recognition. And the nice thing about audio-visual speech recognition is that people have recognized for a long time that there's asynchrony between an apparent asynchrony between the acoustic signal and the visual signal. So if we look at the word here, in case not everybody's a spectrogram reader, the word here is housewives, and these are the lip images that go along with that. So in the spectrogram, if you are a spectrogram reader, here's where the S is. But if you look at the lips during the S, they clearly look like they're producing W, right? So this, in audio-visual speech recognition circles, has traditionally been modeled as 2 different streams, one phonetic and one visual, which are out of sync with each other. But articulatory models actually give us a very natural interpretation of that. Well, why don't we just say that the reason this is happening is because the lips are a little bit ahead of the other articulators. Okay, so that's what we started to do at the workshop with some reasonable results. Still quite preliminary. Another thing that we're looking at is a little bit more work into one of the observation models that I described. So using the outputs of feature classifiers as acoustic features. So this is a generalization of the tandem architecture that's been used recently in speech recognition. And we're looking at doing that using articulatory classifiers. So in terms of future work, we'd really like to know, is there something that we can do with a model like this to actually learn something about speech? So when you actually analyze, when you look at the, say, a viterbi alignment that this model gives you for a given word, it tells you what it thinks all of the articulators are doing. Wouldn't it be neat if we could do this on a large scale and see if it could tell us something about phonology? Similarly, we can actually learn something from the actual parameters that are learned. We can learn, how much asynchrony can occur, how much reduction can occur, how much does it depend on speaker, dialect, and so on. And do the scores that the model gives relate to human perceptual judgment? Can we build a perceptual model of human speech recognition? Okay, And beyond that, there are also a number of different applications that I think related models could be useful for. So one is speech synthesis. So I think it'd be really interesting to know whether you could build a more natural speech synthesizer by modeling the effects of, say, speaking rate or emotion on these articulatory variables. We know, for example, that when we speed up speech, it doesn't uniformly speed up, and some articulators might be slower than others. Another nice domain where there's asynchrony between features is sign language. So when people sign, they have signs that they're doing with different hands, with fingers, with face, and so on. And those things are not necessarily synchronous. And a similar type of model might be useful for that. And then, kind of out of left field, another model that happens to have a multi-stream structure is actual language models for certain types of languages. So for example, there are morphologically rich languages where words can be broken down into multiple morphological features. And an interesting area of work would be to build multi-stream models of these morphological features, similar to factored language models that have started to be built. Okay, and just to sum up, the two main points that I wanted to get across is that we can hopefully do a better job of modeling pronunciation variation by accounting for what the articulators are doing. This is both more parsimonious than phone-based models, as well as having a natural linguistic interpretation. And we've coded these types of models as dynamic Bayesian networks, which are both learnable and also fit into the statistical setting of speech recognition quite naturally. So with that, thank you, and I'll be happy to take any more questions.
So I have a couple of questions. One is about learning curves.
Mm-hmm.
So you might expect that a model that generalizes better would do better at first, but then other kinds of models might catch up. And I know you haven't tested all the kinds of models we talked about earlier, but have you measured learning curves at all?
So what you mean by that is if I had more data,
More training data.
more
yeah.
training data, I might do I might do the same with a less parsimonious model than I do with a more parsimonious model.
Yes, and conversely, if you had very little training data,
Yeah.
then say for adapting to a particular speaker, that you might be able to adapt with less data.
Yeah, I haven't looked at that. I think that would be sort of a natural application of this to languages with very little data, or to domains with very little data.
Or speakers.
Or speakers, yeah.
The other question I wanted to ask about was about second order effects in the asynchrony. So I guess there's a first order question to ask first, which is if you were to cap the amount of asynchrony that you had in your decoder at, say, 2 frames or 3 frames or 4 frames, how much would that decrease, how much would that hurt performance?
Okay.
And then the second order question is, based on the reconstruction that you get by running your current model, is there any evidence that it would help to have second order modeling of the asynchrony at this time affects asynchrony at the next phoneme transition, or where you want to be able to consider this pair of tiers at this time together with a different pair of tiers at this time?
Okay, so on the first point, we have looked at that, and we do cap the asynchrony. So we don't allow arbitrary asynchrony usually. It's not couched in terms of number of frames of asynchrony, but number of states of asynchrony, right? How different can the two indices be? So we can say that they can be right, either the same or different by 1 for an arbitrary number of frames.
Sure.
Okay. And in all of the experiments that I've tried, I've found that I get the best results with up to 2 states of asynchrony. Okay. I don't know if that's a general result or not, but that's been true for audio-visual experiments, for visual experiments, and for the lexical access experiments. In terms of, so context-dependent asynchrony. Right, so you were asking.
That's a fair way to rephrase it.
Right. Is there a difference between the amount of asynchrony that you might see in different parts of the word or different parts of the phrase, right?
Yeah, or if the tongue is falling behind on phone 3, are you likely to expect it still to be behind on phone 4?
Right. So I don't have I don't have measurable results on that, but I have sort of qualitative impressions that I've gotten from, from looking at things like this. And my impression is that yes, that especially as regards word position, it's certainly the case that in certain word positions you're more likely to see asynchrony between articulators and others. In particular, it seems like at the beginning of the word, the articulators tend to sync up, whereas at the end of the word is where you see the most asynchrony.
Do you think
That's again just a qualitative impression.
Do you think there's an interaction with syllable boundaries or morpheme boundaries?
I do think that there's, and I think that this is all very similar to things that have been measured in phonetic pronunciation models, right? We know that there tends to be less variation at the beginning of a syllable than at the end of a syllable, and I think that bears out in these kinds of models as well. So I think that both word boundaries and syllable boundaries are relevant.
Are there questions from anyone other than Jason?
Yes, those are mine.
Okay, last one. Okay, this will have to be the last question.
What is that? What if Professor Meyer wanted to ask a question? I mean, we would welcome it, wouldn't we?
Would we welcome it?
If I wanted to ask a question, I would ask a question.
Right.
I don't want to ask a question.
All right, that means go.
Yeah, is there a way to transfer what you learn in some language to some other language? In some cases, these articulatory features can tell you how something is pronounced in many languages. So have you looked into that?
So I haven't looked into that. I can comment on that a little bit. So I think it's clear that there will be differences between languages. So you can't just port the model from one language to another. So we know that certain things that happen in English, like these stop insertions that I showed, are less common in other languages, and vowel nasalization is less common in other languages, but other effects are more common. So those are all saying essentially that there's different kinds of asynchrony in different languages. What you could use a model like this for is to perhaps predict how a speaker might pronounce words in a new language, in a second language, by assuming that they will carry over some of the effects from their native tongue. I think that would be that's an interesting application to this, is to non-native speech productions.
Could it be that you have a key to the problem of accents?
Yes, it could be.
What I mean is that, I have from Czech, I'm used to transit my articulators in a certain way, and I have a hard time unlearning it. And
You mean a certain strange way?
That's
no, a certain typical way. In other words, that the articulators are unsynchronized in a particular way in one language, and
Yeah, I think it's very possible.
I can give you a little, like a tiny example that might, I don't think anything that extensive is easily done, but in my dialect, there's almost never an M in camp, and there's almost never an M in can't, and that's in a pretty normal pronunciation. And if you could find a variety in which some such allophonic information that's readily represented in your model and tune on it, it might be interesting to look at individual dialectal variations which are easily explained in terms of this feature asynchrony or indexing. It might be fun to try it as a small test, because that's an easy example to show that you stretch the core articulation right to the end of the vowel, and there's no need for closure. I think it's explainable in the feature term.
Absolutely.
As maybe no more than just a cute example, but.
Well, so actually this leads to a twin to the question I asked before about learning curves. Usually when we talk about learning curves, we're asking about the performance on some task like continuous word recognition or something like that. But there's also a question of how much data you need to identify the parameters.
Right. And I haven't really looked at sort of varying the size, but if you sort of think about it, this model really only has, at least the model that I showed in the lexical access experiments only has about 100 parameters. And if you think about,
You know, it's at 100.
100 is mainly these
if you just
surface
look at
to
the
underlying to
pronunciation
surface
modeling,
production.
right, just the pronunciation modeling bit, right? So the probabilities of asynchrony. So if we only allow 1 or 2 states of asynchrony, that's 2 probabilities. And we only allow certain surface feature values given the underlying feature value. So it's actually a really tiny model.
Good to know.
Let me just say that my electrical engineering colleagues are probably not used to unending discussion, are free to leave, but I think we'll continue. It's going very well. Okay, I agree. We'll let it continue for another 10 minutes. No, I know, but okay. No, okay, finish. Mary, go ahead.
So I understand there's a natural extension to the sort of devising kind of thing of your model, but I'm kind of curious about how you see this extending to sign language, where there isn't sort of this natural allowable set of features. What kinds of features would you use in such a model?
Right. So I don't know very much about ASL. I only know what I've spoken to colleagues about, and I've been told that sign language also tends to be described in terms of units, and that these units are obviously not necessarily synchronized between the hands.
Sure, there's a distinct
Right.
picture.
So I mean, those units could be at the level of words, or they could be at the levels of subwords, right? And I don't know exactly what those units comprise.
Well, with sign language, it's going to be a lot trickier to do a DBN, I think, just because you have more dimension.
Oh, yeah.
So you're interested you're not just interested in temporal asynchrony, but also in things getting out of joint spatially.
Sure.
Sure. So there's a tracking problem involved. There's a huge number of interesting vision problems involved.
Yeah, but I don't just mean that. I mean, if I want to say egg, right? My fingers I might do it sort of more carelessly like that. They might not come together in quite the right way.
Right. So your streams might be things like the relative joint angles. So usually people who talk about articulated pose estimations talk about joint angles and 3 joint angles for every joint. And so you can imagine, I don't know how many joints are relevant for ASL, but you can imagine about 3 parameters per joint, something like that, if we're only talking about the forearms.
The other thing that's sort of interesting
It's certainly more parameters.
is it's not clear that every gesture that's in sign language is really conveying word information. It also does lay out some didactic information and so on. So there's more going on in the gestural space in terms of sign language than words. But it depends on the theory. I mean, so there's a variety of ASL theories.
Right, and it might turn out that the best dimensions to model are not these very physiological things, but maybe something more abstract, like a certain entire gesture might be some abstract unit, and it might be more appropriate to model
That's
something
probably
like that.
I think something compositional is there.
Do you have a question?
I have a small question about the feature system and other languages. I don't remember exactly which features you had, but it looked to me like they weren't sufficient for covering some of the things that you'd encounter in other languages, like retroflexion, for instance.
Yeah. So you would have somewhat different feature spaces for different languages. So this one is perhaps appropriate for English, whereas for Hindi you might need a bit more tongue.
So it would be the same articulators, possibly with a few more values.
Right, exactly. Well, it could be also different articulators. So I don't know
Okay,
what click
French.
languages, what articulators click languages use, but there might actually be some other articulator involved.
Okay. Any more questions? Okay, let's thank our speaker again.